Super. Well, great to be here. I wish I could see everybody. I really miss doing these things in person, but it's a delight to have an audience that's spread across the country. And I'm going to pick up from where Jason left off and move into a topic that, yeah, ordinary people don't like to worry about these things. So we have a power system that is constrained by stability. So I adopted this cartoon. This has been used for power training power students for many decades, and this is a visualization that non-engineers or people that don't live in this space all the time can usually get their hands around. So the power system is this organism that is dynamic, and this little mechanical visualization here is it gives you a pretty good sense of what we worry about. We power nerds worry about when we talk about transient stability. So what you see here is the idea that these different spheres are masses that are the synchronous generators of a traditional transmission system. So this is the old world view of this, and the power system is connected together by transmission lines. And each of these lines on this drawing here are representative or cartoons of transmission lines. And the length of the lines is representative of the electrical distance. The fatness of the lines is representative of the voltage level. So you have, if you want to also mix this imagery with a highway system, the fat lines are major highways, the skinny lines are minor highways, and all these things are stretchy. It's important to get that mental visualization of it. So when the system is in equilibrium, when it's purring along from minute to minute, there's very little motion, and all these things are sitting there. And as we add generation, at some point, it stretches the rubber bands near those points. If you stretch them too much, they break. But for the most part, we don't worry about them breaking that way. What we worry about are acts of Mother Nature. So the pair of scissors is a representative disturbance. We have, right? We power engineers live in an N-1 world. The power system is designed and operated so that one bad thing can happen, and effectively without any human intervention, we can tolerate that one bad thing. So picture in your mind the snapping of that rubber band that's in the drawing. You can imagine this whole thing bouncing around, okay? And it'll bounce around, and so in the remaining rubber bands, some will be more stressed, some will be less stressed. And if it comes to a new equilibrium, if it stops bouncing around and nothing else breaks, and the condition that it's in after the bouncing stops is satisfactory, that's a stable system. If, on the other hand, the act of bouncing causes more of the rubber bands to break and the system cascades, that's the language we use, into failure, we have a failure of transient stability. So a lot of people like this cartoon, some people hate it, but it's a lot better than me throwing differential equations at it. So this is the world that we have been planning and working around for decades. The system is, our power systems in the US, and I deliberately left out Texas because we've got Julia, the expert, to talk about that, but here's a drawing from 25 years ago. And you see this web on the left. This is a map of the Western Interconnection, and you see the transmission as it existed 25 years ago. And the colors in that, those 5 colors are where the system broke apart after a particularly violent event. You see a time trace on the right of the system failing. And there's a couple things to learn from that. First of all, the failures happen pretty fast, right? This is ones of seconds. The whole event's over in less than a minute. the system broke into 5 pieces. This is relevant to Jason's cartoon earlier on about frequency control. All right, so in '96, some of those colored squares were viable and the light stayed on, and some of those colored squares were not viable. There was no way to keep the balance between generation and load within a reasonable bounds, and they went black. So a couple things. It's a nice visualization. This is an issue that isn't new to the transformation to inverter-based resources, wind and solar. We've been living this world, especially in the West, especially in Texas, for decades. But I'm going to get there. It starts to look different. So in the East, this is I picked this drawing out for some interesting work, looking at how that rubber band system behaves. And what you see in this particular drawing, and I picked this because I like the way the red lines on this sort of remind you of the cartoon. This is the entire northern part of the Eastern Interconnection during an event, and the measures here are how hard those rubber bands are stressed. So again, 2 important points. Both these systems, as well as Texas, are stability constrained. Particularly in the East, the really big interconnection, the main issues are at the edges. So I said that in this slide over here. So keeping New England and the Maritimes stuck to the Eastern Interconnection, keeping Florida stuck, keeping the Southwest reaches of SPP, and keeping the High Plains connected are more challenging technical issues today than worrying about what happens right in the heart of the system. And that is going to continue to be true, especially as we add wind and solar to the edges, where there's great wind on the west side of the Eastern Interconnection. There's wind in the Maritimes. We're talking about gigawatts of offshore wind off the eastern seaboard. Those are at the edges. So the stability issues that we've always had are going to be there, and they are going to look different. And this cartoon is an adaptation that I made from that original cartoon, as I said, that was originally published by a guy named Elgard in the 60s and has been reused for power students ad nauseum. But my little cartoon here shows wind and solar not as masses, not as blue steel balls, but rather as hands. And I apologize if it's too childish, but Jason said this repeatedly. The behavior of wind and solar as it relates to the grid is all about control. It's all about brains. So the mission of a wind plant or a solar plant is to get power into the grid, and they don't want to do anything else unless you tell them to. So when the scissors cut the system on the left, this thing bounces around, but the hands' first reaction is that they would like to go for a ride. They don't want to bounce around. They don't have weight. They have no inertia. You've heard that? People worrying about lack of inertia. Julie will talk about it some more. But that is a two-edged sword. The fact that these things don't like to bounce around like the dead weight of a synchronous machine means that the system behavior, the way this system bounces around and the way it fails look different. And we've been working as an industry on that distinction very hard for close to 20 years now. So we've learned a lot, and we're going to move on. So this is a figure, I've been using this for many years. This is actually a simulation of the same plant that Jason showed that had the nice voltage behavior. And there's 2 different examples here that are supposed to be apples to apples comparison. So this is a simulation of a large power plant at the edge of the Western Interconnection. And the black lines are a simulation of a wind plant. Again, this simulation was done 15 years ago. The hand, right? My hand in the previous drawing doesn't like to bounce around. And you can see in the black traces on the left, the system gets clobbered by Mother Nature with a lightning stroke. The lightning stroke is cleared. That's what that notch is. That takes a few hundred milliseconds. It's really fast stuff. And then it comes back. The red curve is the bouncing around of those steel balls in the previous figure. Power system nerds recognize this figure. They have spent years making sure that the red bouncing is well behaved and the system comes back. So the pair of curves on the left is a success. The pair of red curves on the right is a fail. The event was too violent and the steel ball ripped off in the red trace. The wind turbine, in this case, didn't. So what I want you to learn is that A, the behaviors are quite different. B, in some regards, the behavior of the wind and the solar, the inverter-based resources, are vastly better, and we can tend to load the power system up more, but the way it behaves is radically different. So we've got a bunch of new learning, and we need some new tools and some different criteria to make sure that we understand the black behavior and how it breaks, because it's not the red trace anymore. As I have laughingly said occasionally, right, we're not in Kansas anymore, but maybe we are and it's just windy. So the next piece of this puzzle is related to that previous thing, and that is, okay, the system, as I just showed you, tends to be stronger, more tolerant of disturbances. So economics and human nature dictate, if it's tougher, let's lean on it harder, right? We push more power through, we'll get more power out of the wind plants, we'll get more power out of the solar plants. That's good for everybody, for the most part. But what happens when you push it to failure? You can never go to infinity. And this is some illustration of a system being pushed to failure. And what you have on the right are three traces that are three cases. This is in the eastern part of the Western Interconnection in some future system with lots of wind and solar, where we have pushed more and more power out of the wind and solar and taken off more and more of the existing thermal generation, right? That's the trend. The zero marginal cost renewable resources tend to displace the fossil thermal resources. You all know that. And it changes the dynamics. But this is a cautionary slide. In the blue case is very successful. System works beautifully. You hardly even notice that it's been upset. Lean on a little more, the red case is still really good, and it would meet our criteria. You lean on a little bit more, and the mental image I want you to have is that it shatters. Okay, so the failure modes of the system with lots and lots of inverters, as we're trying to push power from the edges to where the load is, start to look a little different. ERCOT's got immense experience. This is a little bit cartoonish still, but what we have now is a reality that you as regulators need to recognize, and that is that many aspects of the behavior are desirable. The system tends to be, in some regards, not all regards, in some regards, it tends to be more disturbance tolerant, and therefore the economics say lean on it harder. And the practice of reinforcing the system so it doesn't break, and knowing when you're at the brink and knowing when you need to de-stress the system is a work in progress. We are vastly smarter than we were a decade ago, even 5 years ago, but this is in that space that Jason talked about as we keep pushing that envelope of how hard and how much of the resource at any time can be inverter-based. Okay, so this is a brain-meltingly complicated tool figure, but it's got a couple of quantitative things that I want for you to that are relatively simple for you to take away. We aren't alone in the U.S. And as I said, Texas is leading in many regards in the U.S. We've got some very interesting stuff going on in Hawaii, but in many regards, there's things to be learned from outside of the country. And Ireland is one of the places to watch. So Ireland has the most aggressive renewables targets, the most aggressive decarbonization targets of a single system in the world. So people talk about Denmark, but Denmark's little. They're connected to big Europe. Not to be dismissive, they've done great things in Denmark, but for the most part, they lean on their big neighbors to get through their problems. Ireland can't lean on anybody, they're an island. And this curve here, and I warned you, it's really complicated, but the essence of this curve is left to right is more wind, more batteries, more HVDC, less fossil generation. And the vertical axis is a metric of pain. I'll just leave it at that. Red's bad, green's good. This curve, which people have called the J curve in Ireland, is representative, not precise, representative of behavior that much of the industry has observed in other places. And that is, you see this, these dots all over the place. So there's a lot of variation, there's a lot of nuance. This is just Ireland. Those are many, many different operating points, but the people in Ireland, a guy named John O'Sullivan is kind of famous amongst us nerds, sketched in this J curve. And the thing you want to learn from this curve, and consistent with behaviors that we've seen in many places, is that the behavior gets better as we add inverter-based resources up to somewhere around 50%. And then it starts to get a little funky and we start to lose some of those benefits. And somewhere in the neighborhood of 75, and you know, I deliberately don't want to use a precise number, but somewhere around 75%, the dynamics, all these things that I've been talking about that look different, start to cause significant discomfort and in some regards, the brittleness that I showed. So what do I want you to learn from this? Most of the country, most of your constituent systems are somewhere most of the time below that 50% mark. We know how to do it. We can go forward. As we get to the edges, as we add more and more inverter-based resources, and think of Jason's figure from early on in the talk, there will be some hours where now we are starting to move up the edge of that J curve. And you know, Jason gave an example. SPP hit 84% on approximately this axis. Successfully. So they were somewhere in the orange, they did it. ERCOT occasionally is up in the 60 to 70% number. They're doing it. That's still down in the green. They figured it out. But Julia stays awake at night, worried about what's going to happen when she moves further up that curve. Solving that problem for the most part is not your concern, but recognizing that we don't need to put the brakes on as we move across until we get way out to the right is important, because while there's some hours that us nerds are trying to figure out how to deal with, most of the time and in most of the country, we're still in the green. So good news, but no complacency allowed. So this is a summary of those points. We have always had transient stability problems. They look different now. For the most part, they tend to be better there are exceptions, and the fact that they're better is to some extent nice, but we just push the system harder, or find other, and I don't want to make that an absolutely cast in concrete. There are some behaviors that the IDRs are not as good, and the industry has been getting these progressively better. And in truth, we don't know all of the details of how all these pieces work together under all conditions. So we're still, as an industry, on a little bit of a journey. There are a multiplicity of technology, traditional solutions that make that all these cartoons that I've shown you better behaved. So there's an arsenal of existing solutions. We put more lines up, we add various reactive compensation, we add synchronous condensers. We can come back and talk about that later if we have questions. And then there's a host of new technologies making the inverter-based resources better. We're going to talk about grid forming briefly in this talk. So each of these are new tools being added to an existing arsenal. So again, generally not a showstopper. Complacency doesn't work. We have an arsenal of tools. Some of the tools are relatively cheap. Some of the tools are relatively expensive. And some of the practice is frankly not familiar to all the participants. So we need to constantly be pushing, and that's one of the reasons why we're having seminars like this. Okay, so having said that, let's get into a different related face of the system behavior. And that falls under this useful blanket term of grid strength. And you may have heard people talking about weak grid issues. So this cartoon was put together, I think, by Matt Richwine a few years ago, but you see variations on the theme. The idea, right, with my cartoon, the system bounces around and gets clobbered. Well, the trampoline here needs to be strong enough to tolerate the disturbance of our acrobat on the right bouncing on it. And as the relative weight of the acrobat gets bigger, or the number of springs at the edge becomes less, the ability to tolerate and get predictable behavior out of the bounce drops. So this is, again, you know, either you love cartoons or you don't, but this is the electrical analog of grid strength. And we spend a lot of time trying to make the acrobat better behave so it doesn't clobber the system so much, and looking for ways to get the springs back in. So it's two-edged. Disturb the system less, make it, and find ways to make it stronger, and find other ways to make it tolerant of the perturbations. So this is a list of things that contribute to grid strength. So on the left are a bunch of technologies that mostly you will recognize that make the system strong. So, you know, read across the top. The first thing is kind of obvious. Add more springs, add more blue lines in my cartoon, add more springs on the trampoline. That's what makes the grid stronger. As a country, we are going to need to build new transmission, but we need to augment the strength that comes with the transmission with a variety of other approaches. Running synchronous generation provides that strength for this class of disturbance. So if you only need to run them every once in a while, maybe that's the right answer. But as Jason Keats showed, and we showed the trends, more and more hours of high stress in which the generators are not there and the inverter-based resources are dominant means that we have weak grid problems more and more frequently, And solutions that might work for a few hours a year economically don't work for hundreds or thousands of hours. So we might end up using the synchronous generators on the left differently. We can add surrogate generation in the form of synchronous condensers. A synchronous condenser is a generator without a turbine on it. That provides the strength. And then we can make the next generation of inverters better. And that's a work in progress today. But please to remember, right, when we talk about weak grid, we start throwing things that are inverter-based. They do not strengthen the system. And frankly, now I'm giving this slide, in addition to solar PV and wind and battery energy storage systems, for example, HVDC transmission doesn't add to system strength. And some types of voltage control devices that use inverters don't add to system strength. So that list could actually be a little bit longer on the no side. Okay, so, gee, that's kind of scary. How do I know when I'm at risk, when my trampoline doesn't have enough springs or the guy that's bouncing is too fat? And there's a number of different metrics. Most of those are related to, or some variation of, the so-called short circuit strength. And I won't give you the math, mercifully, but the measure, short circuit strength, is a quantitative measure of how strong the system is relative to how big the inverter-based resources are. Okay, so a strength, a system of a given strength with a little Acrobat does fine. A system of the same strength with the Acrobat gets much bigger, doesn't do so well. So it's all relative, and that's what these short circuit ratios are. That's the first point. The second point is, and ERCOT's done some really good pioneering work, as some others have, is you can't look at the strength by looking at each individual Acrobat on the trampoline. Because the reality is that we got a whole bunch of inverter-based resources bouncing around on that trampoline at the same time. So there's been there's a growing body of practice that looks at the aggregate behavior of all the things and says, is the trampoline, is the system strong enough? Those are good tools for sort of flagging, okay, be careful, you're in the soup. There's a lot of nuance that goes with that. And the industry is getting better. As I keep saying, ERCOT's some of the leaders in this, but there's different ways to tackle that. So so what? So why do you care, right? If the system is too weak, you end up with those brittleness problems that I showed. The system will not behave well. It will not tolerate big disturbances. In fact, it might not even tolerate little disturbances. So we need to understand that. We need to understand the most effective way of reducing the risk by strengthening the grid and reducing the intensity of the disturbances that make it misbehave. And those are hard arguments to make. It's like, okay, we need to spend ratepayer money on because we got a weak grid problem here in rural Kansas. Say, what is that? What are you guys talking about? Well, this is what we're talking about, and this is real. And I'll show you a couple of real things that are a little scary. So one of the ways to move forward, and Jason made allusion to this, is to capture the aspects of the synchronous generator, the thermal generators that are getting pushed out of operation, to capture the attributes of those machines that are grid strengthening. Not all the attributes, but the grid strengthening attributes with the inverters. And at the risk of making this too simple-minded, that's what we're talking about when we have so-called grid forming inverters. So for your reference in this audience here, all the commercial wind and solar in operation in the US today, and all the stuff that is being purchased as I lecture are grid following. They are those acrobats, and they have an expectation of a minimum grid strength. They're getting better. The industry has made huge progress in making them better behave and tolerating progressively weaker systems. But it's an issue of diminishing return. So we're looking here at a paradigm shift to grid forming. This is shifting from the blue curve of Jason's earlier curve to the green curve. And that's one of the faces of grid forming. Grid forming then becomes an active element, all right? It behaves fundamentally different, and the industry is working on that. I'm going to show you some promising stuff, but it's not, aside from being available on batteries, not wind, not utility scale solar yet, but on batteries, it's not ready yet. So maybe I won't spend time on this slide. There are some differences in the way we are going to, the industry is moving to make grid forming inverters capture the good aspects of synchronous machines. So you're going to hear this if you're listening. There's a sense in the industry at the casual, to the casual observer, to the casual listener, and I don't want to accuse you, audience, of being casual here, so maybe that's a bad choice of words, that the removal of the conventional synchronous fossil generation and replacement with inverter-based resources is uniformly negative relative to system behavior. I've already shown you some examples why that's not true. Relative to system strengthening, that is true today. It is possible. It is technically possible. In fact, we, the industry, know how to make inverters mimic synchronous machines. All right, we could do that in an instant, but it is a relatively poor use of money and capability. The reality is that the inverters have agility attributes that are vastly superior to the iron and copper of a synchronous machine. So the trick that we are in the middle of a journey on as an industry is to capture the desirable attributes of the synchronous machine, leave behind the undesirable attributes of the synchronous machine, capture the desirable attributes of the grid following inverters of today, and cancel out the undesirable attributes of that. So we are not looking to just go back to the past and say, okay, we could just make the inverters look like the old stuff that we knew about. That is intellectually and lazy and economically suboptimal. So we're on a path as an industry to move forward to a future that is better than the one we're leaving behind, not just to address some of the new problems that we are creating in the course of the journey. I can't say that with enough fervor. So there you go. So this is a cartoon that I worked up recently to try to get you a little sense of the fact that there is a continuum of challenges. So some of these things that you've seen today, like the brittleness, are a little scary, and the trampoline breaking and the lights going out. As I keep saying, we can't be complacent, but there's a spectrum that I've put in this particular case on a scale that's geared towards the so-called short circuit ratio. I didn't want to emphasize the numerical aspects of it, but most of what we're doing today is still in the green zone and starting to move into the yellow zone. We know how to do stuff. You can plug and play in the green. You can with commercially available, well-established technology, get the system to work in this area that I'm kind of saying yellow, where there's a lot, right? You heard examples today of operation. But as we go way to the right, to the endpoints, where asymptotically we approach 100% of inverters and nothing synchronous, we need some new tools, and that's still in the red at scale for large systems with commercially available proven technology. We're going to get there probably fairly quickly. There's across the bottom, without belaboring it, there's a spectrum of progressively more esoteric and less mature tools in the hands of the folks that are working on planning and operating the system. That's what I'm getting at across the bottom. The tools need to accompany the evolution. So as the technology moves along, the tools necessary, right? We can't have the planners or the system operators flying blind. So we're getting better at that. And this is going to be a journey that we're going to be on for many years yet. Okay. Many of you are market designers, regulators. The mechanisms, the market mechanisms to make sure that the trampoline is stiff enough are in many regards unclear. These are generally related to more traditional things like wires, all right? So contributions to making the grid stiffer, if you put in a better inverter in your wind farm and add to the grid stiffness rather than degrade it, there isn't any market mechanism right now to reward you for being a good citizen. So we've got various carrots and sticks, but right now it's a work in progress. So there's a bunch of things in this shopping list that we can do that fall into different kind of color money and different regulatory buckets. And we got to pay attention, and the folks on this call need to pay attention to the fact that the imperatives look different and the list of options look different, and the participants that can make a positive and economically sensible contribution aren't the same, necessarily all the same players that they always have been. Okay, so now I'm going to go into the really complicated stuff.
Nick, this is Debbie. Can we take a quick break? We were going to take a short break
to take a break.
Talk.
Okay, so I'll resume in 5 minutes?
Sure, that sounds good.
All righty. Well, while everybody is getting their brains back in, I will start this pretty nifty video if I can get it to work. There we go. So the next topic is small signal stability, and if you thought that transient stability was a nerd's paradise, the small signal stability is even more esoteric. But hopefully everybody has seen this over their lives, right? This is small signal stability in a most real fashion. So this is what happens in mechanical systems when we have a small signal stability problem. So this bridge was stimulated and at a frequency, stimulated by the wind at a frequency that it couldn't tolerate. Well, power systems have stimulation that is happening all the time, and if they have natural electrical vibrations that you can visualize with the bridge coming down, they can misbehave. So this is an issue that's been around for a while, but there's a bunch of, and we have dealt with them. I got a bunch of language on the left here, but the key point is, again, just like transient stability, it's not new. Some of the issues that we have today are very familiar looking. Some look familiar, but have different root causes, and those some of those related to the behavior of the inverter-based resources look like what we've always worried about, but actually have different root causes. And as an industry, we're getting smarter about that, but these are things to worry about. And you can see this doesn't actually add too much, other than to note that from a regulatory and a rules point of view, there are rules in place to mandate mitigation of bad vibrations that have been there since the 60s for the ones that we recognize. Institutionally, we don't have the new rules in place because we don't have an experience to know which ones are systemic and common and really need rules or a one-off. So that's kind of a little bit scary. This chart is one that only nerds could love, and the only thing I want you to learn from this is work that I did with a colleague 15 years ago when we were starting to worry about this problem. And this is specifically addressing the idea that the traditional poor damping problems that I showed on the previous slides might be exacerbated by inverter-based resources. And there's way too much information on here other than the red arrow is the stress on a traditional synchronous, thermal-based system being increased and the behavior getting worse. And apples to apples comparison in this particular case, increasing the stress with inverter-based resources, the behavior actually got better. So what that says is that the old mechanisms that we always worried about, we probably don't need to worry about, but we may need to worry about new ones, and I'm going to go on to that. And one thing that we worry about and have always worried about is the fact that the existing generation, particularly the thermal generation, are big, heavy mass spring systems. Okay, so there's different turbines. There's high pressure turbines, low pressure turbines, and generators. And these things make a big, long hot dog with masses on them that bounces around. And when the power system wallops this torsional system from the outside, it bounces around. So this is the hot dog version of my earlier cartoon, and we got to make sure that we don't damage the equipment. So what? Why am I putting this up? When we add controls that are very responsive, they can interact with those machines in ways that are undesirable. So I got this little cartoon that is the electronic version of that bridge going bad. And who has not been in a room where somebody screwed up the gain, right, the volume on the microphone, and it fed back through the speaker, and bad news. That's positive feedback. We don't like that. And that can happen in a power system. Here's a very old but real and terrifying example of a steam plant in the Western US being subject to that little boy putting his hands over his ears. So this lower envelope is actually a field measurement of the vibration, the torsional vibration on that fossil plant growing because somebody got the microphone too close to the speaker electrically. We know how to deal with that, but the industry history is generally with great big discrete pieces. This problem was caused by a gigantic 2,000 megawatt HVDC terminal, and we fixed the controls on that. But when we're talking 10,000 megawatts of wind and solar that's spread across 100 different plants, we aren't 100% that we have all the issues resolved on that. So this is kind of a cautionary note. So old worry, new manifestations. You as regulators don't need to understand the nuances. There aren't very many people actually even in the industry that understand all the nuances. We don't understand all of them, but it can drive both risk and the necessity to, for example, limit operation, the necessity to change controls, the necessity to reinforce the grid. So these are real things. So as we move forward here, I've laid a bunch of things that are kind of scary out, and let's talk about how these things fit together. So we talked about moving left to right, or progressively more. This is the same left to right that we keep using. More and more power electronics, more and more inverter-based resources, higher and higher fractions, up to a world that is possibly 100%, at least at times. And this kind of captures, in summary, many of the things that I introduced and that Jason introduced for making the system behave. So as we move across, we keep moving into different risk regimes. This is also that same cartoon where I went from green to yellow to orange to red. And we need new solutions way off on the right that include, for example, grid forming inverters. So I don't want to terrify you that we don't know how to fix these problems. There's a long list of successes, many of which are being deployed, but truth to be told, not uniformly. So there is an institutional issue. It's true for all institutions, so I'm not picking on ours, that demands the dissemination of best practices. And, you know, I get embarrassed about how much I praise ERCOT because they've got a lot of best practices. You saw prima facie evidence that SPP is doing a whole bunch of things right. MISO is doing a whole bunch of things right. Xcel Energy is doing a whole bunch of things right. Now, but they aren't doing all the same things right. And we need to make sure institutionally that the laggards are paying attention to the way to do things right, because it results in a more reliable, more economic system. So there's this list of currently available technologies and methods that are being used, in some widely, some less widely, that I've talked and that Jason have talked about repeatedly today. We need to make sure that all the tools that are available in the arsenal today are being used. All right, so The last one on this list, right? So I keep saying that we have made the inverters vastly better. And I'll give you a for instance, right? Those color charts on the short circuit ratio. A few years ago, less than a decade ago, we would have been terrified at the idea of having the system operate below short circuit ratios of 5. Now we don't even blink around 3. At 2, we're on like the, oh, be careful track, okay? So the industry is getting better and better. There are other ways to stiffen the system with more transmission, packing more power onto existing lines, ways to, and adding stiffness by synchronous condensers, and moving the power around and in real time being sensitive and creative with understanding what the system limits are. There's a bucket of technologies that are being lumped together as grid enhancing technologies. Those are all ways to make the wires work better. So as we move forward, we've got a spectrum of capability and gaps. I think I've covered this pretty well. I got one or two examples to go through, and then I'll wrap up. This is an example. So this is intended both to be good news and bad news. This is a small signal failure that caused a blackout last year. I guess not last year anymore. 18 months ago in the UK, in which a gigantic wind farm, one that was under construction to be 1,600 megawarts, wasn't did not have the weak grid controls enabled. And there was an event nearby that weakened the grid and drove this wind plant into an unstable, small signal unstable. And what you see in this trace, these are real traces of a couple of violent swings resulting, and then the system broke. And the blackout took out millions of customers, 1 billion customers, some of which was very ugly. So the cautionary note here is that if you're not paying attention, you can get in trouble in a hurry. This is the proof that it was actually a small signal event. These traces were from a tiny event that occurred 10 minutes before the system went black. And you see those swings are very ill-mannered, right? They're barely damped out. And that was for a little tap, all right? The plant was in construction. It had off-the-shelf controls. They shouldn't have been running that way. After the blackout, the OEM went out and said and upgraded the controls basically within a day and removed the issue. So is this good news or bad news? Somebody wasn't frankly paying attention, and they had an ugly blackout. The problem was mitigated with available technology. So, you know, is this a half full, half empty example, whatever you want to call it, it's real. So the last thing I want to pass on is some new work to give you a sense of the current state of the art. This is work that I and a colleague did. We are not, by any stretch of the imagination, the only people working on grid forming inverters. This was specifically an exercise to look at what I personally and many people regard as the most pressing dynamic performance issue facing us in the near term. So I want to drive this home for you audience as I put it at the end. We are looking in the near term about building a lot of these inverter-based resources on the edges of our system. Julia's already doing it in the Panhandle of West Texas. SPP is already doing it on the western extremity. MISO is doing it up in the Dakotas. We're going to be doing it in the east offshore. The issue of making sure that we can get that power to the load centers is much more pressing than the whole list, the grid-wide issues associated with frequency, et cetera. And this example is the last thing I'm going to show today. It goes from left to right, 3 columns of the system being soft. I don't want to call this a stiff system because it's not. Historically, we would have called that very weak. Now it's just soft. The middle is the current limit of our technology today, about, okay? So we can't really do better. And then on the right is weak grid beyond in terra incognito for us today. Across the road these are all the same system trying to push power out of something like the high plains or off the or the Maritimes or the ends of Florida, pick your example in your head, into the grid. And the top row is using inverter, today's best in class grid following inverters. The middle is using today's best in class synchronous resources. And the bottom is using one possible implementation of grid forming. Do not make the mistake of thinking grid forming only means one thing. We aren't there as an industry yet. But this is pretty cool. The outlines of the boxes tell you the results. On the left, everything works. That's where we are today. In the middle, we stay away from pushing the system this hard. The yellow boxes are marginally stable. With grid forming inverters, with this variety of grid forming inverters, this works beautifully. If you push even farther, this is one way the system breaks. We're very familiar with the way the synchronous generator breaks, less so with the grid following, but for grid forming, we get really nice behavior. This is not an ironclad case. This is institutional learning.
We need to wrap up.
Yep. Sorry, I promised I wouldn't do this to you, Julia. Okay. We need more transmission regardless of what we do with the inverter-based resources. We need to do better with both the new transmission and the stuff we've got. And we've got to make the system stable. All right. There's lots of different faces. You heard those from Jason and I today. Some things get better, some things get worse. We have a lot of tricks in our arsenal, and there's more coming. So sorry, I rushed that last little bit. Julia, you're on.
Actually, Nick, I'm going to ask you one quick question and then switch it over to Julia. So the one quick question is, would you discuss the impact of the new 500 kilovolt line coming down from Manitoba Hydro into Minnesota? How much would that help things like stability for the Eastern Interconnect and Minnesota in particular?
Well, it's a speculative answer, first of all, because I've not studied it. Sharing resources is a really, really good thing. So more transmission is better. Every time you add a new transmission, especially a long one from the edge, you do introduce stability constraints. The transient stability question of keeping Manitoba stuck to MISO, I'm sure, is front and center in the design of that. It won't be, there's going to be some constraints. I'm absolutely certain it will be a net positive, but it's not something that's done lightly. And I'm sure it's not being done lightly. So, yeah.
All right. Thanks.